Hey everybody, welcome to Notes Video K, Section 3.9, Linearizations. A linearization is a tangent line that is used to approximate functional values on the function that we're writing an equation of a tangent line for. So when you see linearizations, all it is revisiting some of the things we've done, writing equations of tangent lines, and then using that tangent line to approximate y values. So let's just first start by considering a graph of what we're going to be looking at. If you will, consider over here, pardon the graph, it's been a while since I've actually done anything on the video, so I'm out of sync here a little bit. I want to take a look at the function f of x equals the square root of 1 plus x. Okay, if we look at a graphical approach of that, the square root of 1 plus x would start here, and it would continue in this manner right here. Okay, if we're interested in the tangent line to this function at x equals 0, we're interested in this point right here, this point of tangency. This would be x equals 0, and if we plugged in 0 to the function, we would get the square root of 1, which is just 1. So let's kind of look at our behavior near 0, 1. So what we want to do is we want to write an equation of a tangent line to the graph at this point right here. Okay, so we're going to come over here, we're going to create this linearization, if you will. Okay, so what we need to do is find the derivative. So rewriting the radical, using the chain rule. Derivative of the outside function times the derivative of the inside function, which that derivative would just be 1. So this completes the derivative. So we're trying to write the equation of the tangent line to the graph over here. So we need the derivative and we need to evaluate it at 0. So I'm going to go ahead and kind of clean this up. It makes it easier to evaluate. So 1 plus x underneath the square root. So let's find the slope of the graph at 0. We know that it's going to be a positive slope. The slope of the graph is positive because the function is increasing. So let's plug in 0, and if we can do that right up here, we see that we're going to get 1 over 2, 1/2. Okay, so to continue writing the equation of the tangent line, let's just make sure we remember that we're using the point 0, 1. So this is our x, this is our y, and this, of course, is our slope value, our m value. So let's use point slope. And then, of course, we're going to have x minus 0 here. If you wanted to go ahead and put it in slope-intercept form, clean this up a little bit, we're going to have 1/2 x plus 1. So that's the equation of the tangent line to the curve here. All right, so that's a tangent line. We can also call that a linearization. If we're going to use the tangent line to approximate functional values near the point of tangency, we're talking about x values near 0. So if I moved over here to say x equals 4, 4 is too far away for what I'm wanting to do here. If I want to kind of figure out what the y value is on the function at, say, 0.1 or 0.2 or 0.3, as long as I'm relatively close to the x-coordinate of the point of tangency, we can use the tangent line to approximate the y value. As you can see, the graph and the tangent line intersect at x equals 0, but after that, to the left and to the right of x equals 0, the tangent line moves away from the curve just slightly. And of course, the further you travel on the curve, the further away the tangent line would get. So, you know, using a tangent line to approximate a functional value is really only good if you're close to the x-coordinate of the point of tangency. Okay. All right, let's just kind of look at this graphically right here. If I wanted to approximate the functional value at 0.1 using this linearization or this tangent line, what that would mean is I would just plug in 0.1 to the tangent line equation. So half of 0.1 or 1/10 plus 1. So the y value that we're going to get is going to be 1/20 plus 1. Okay? Or if I wanted to clean that up a little bit, get a common denominator, I can say that I'm using the tangent line to approximate what the y value is on the function here. It looks like that's going to be 21/20. Now, of course, I can actually find the actual functional value by plugging in 0.1 here, adding it to 1, and finding the square root. And that would be relatively close to this value right here, 21/20. But let's get a graphical look at it. If this is x equals 0, let's just consider that this is x equals 0.1, what I plugged in over here. If I travel vertically to the curve, if I travel up, notice that I would, first of all, I would intersect the function first. So it looks like this functional value right here, if I'm on the curve, is going to be a little bit smaller than, say, the y value on the tangent line. So what we can say from this is that the tangent line over approximates is a greater y value on the tangent line at 0.1 than it would be on the function itself. And a lot of times they're interested in knowing, well, why is it? Why is it that the y value that you get out of the tangent line equation, why is it that it's greater than or above, if you will, the actual functional value, the point that's on the graph? And you can see clearly from this graph right here that the graph is concave down. As the graph bends downward, the tangent line is going to be located above the graph itself. So, the y value on the tangent line is going to be a little bit higher than, say, the y value that's on the function. Okay. So, and the further away you move, if you stay on the tangent line, you can see that this y value on the tangent line is going to be greater than this y value that's on the function at this particular x value right here. So as the tangent line moves away from the graph of the function, it's not a good idea to approximate this y value on the function if you're on this part of the tangent line, which is far away from the point of tangency. So we want to stay pretty close to the point of tangency if we're going to use a tangent line to approximate a y value that's on a function. If I wanted to find an approximate functional value on this function, say at 4, then probably what you would want to do is you'd want to write another equation of a tangent line at x equals 4. I wouldn't use this same tangent line here because it's moving quite far away from the y values that are on the tangent line that are close to x equals 4. Now that we're kind of finished with this example and kind of looking at a linearization and just knowing that a linearization is just writing the equation of a tangent line, but then one step further plugging into the equation for a tangent line an x value close to the point of tangency. Now that we've kind of seen that, I want to look at kind of another quick example of something that you might be asked in regard to this topic here. Let's just, for example, make up another function, just as disconnected from this problem right here. But let's just say that we have, an upward opening parabola. And let's just say we're interested in the point of tangency at x equals 1 to this function. So, we went along, we wrote the equation of the tangent line. Okay, and let's say that we're asked to approximate the functional value, the y value on the parabola, at, say, x equals 1.1. So I'm just going to kind of pick on this and say, well, this is 1.1. And I know it's not drawn to scale, but it's kind of hard with a graph to be able to see it here. So just, if you will, just allow this to be 1.1. All right, so if I'm at 1.1 and I've got this equation of this tangent line, and I do have the function too, as I travel from 1.1, notice that I'm going to intersect the tangent line first. So this y value on the tangent line, and if I kept traveling, is going to be underneath or smaller or less than this y value that's actually on the function. So if you're asked, in this situation, you've explored this problem, if you're asked, is this approximation on this tangent line, this y value, is it less than or greater than the functional value? All you have to know is something about the concavity of the graph. Notice this graph is concave up. So if a graph is concave up, the tangent line is going to fall below the graph. And so if the tangent line falls below the graph of the function, then this y value is going to be smaller than the y value that's on the graph. If you remember back up here in this example, that when we had this y value on the function, its comparison with the y value at that same x on the tangent line, this y value, the approximation, was greater than this y value right here because the graph of the function was concave down. The tangent line is going to be above the graph of the function. So I just wanted to kind of look at both situations when you have concavity upward and how your approximation is smaller than, less than, and under approximation of the y value, and concavity downward, which would mean the approximation on the tangent line is above or greater than the y value that's on the function. All right, so at this point, let's do an example from the textbook. So if you guys want to pause the video, grab your book on page 240. We're going to do problem number 3 together. All right, for this particular problem and the problems 1 through 6 in this particular section of section 3.9, you can see that the directions say find the equation of the tangent line t to the graph of the function f at the given point. Use this linear approximation to complete the table. So I'm going to do example 3. It's the x to the 5th function, and we have a t-chart here. And we want to write the equation of the tangent line at this point right here. So let's go ahead and get that out of the way. Okay. So let's find the derivative. It's evaluated at 2. When we plug 2 in here, boy, this graph's going to be pretty steep. So the slope of the tangent line at x equals 2 is 5 times 16, which I believe is 80. So writing the equation of the tangent line using point slope, and I am going to go ahead and solve it for y. I'm going to leave it in this factored form though. I'm not going to distribute the 80. You'll see why. Okay. All right, so we've got the equation of the tangent line to the graph at 232. So let's kind of get a real quick picture of what's going on here. I encourage you to graph x to the 5th, and it actually looks like x cubed. So it looks something like this. So at x equals 2, perhaps right here, if we looked at the point of tangency at x equals 2 and drew in the tangent line, you can see that the slope of the graph is very, very steep there. It's going up very rapidly. So we'll kind of work with that tangent line there. Okay, so over here we're asked to actually find the actual functional values on x to the 5th at these x coordinates right here. So I do x to the 5th using my calculator, and I got 24.76099. Okay, now I'm going to evaluate the function at 1.99 to find that y coordinate. Well, it's 31.20796. 20796. As you might imagine, when you evaluate the function at 2, you're going to get 32 because that is the y coordinate. Okay, when I plug in 2.01, okay, the y value on the function's increasing, so it's 32.80804. And when I plug in 2.1, I'm moving a little further away from the x coordinate of the point of tangency, so my y value should actually be a lot higher than 32, and it is. It's 40.84101. So these are all the y values that are on the function near x equals 2. So by using the tangent line instead of actually finding the functional values, let's see how close the y values are on the tangent line. So let's go ahead and plug in 1.9. So notice that here when you plug in 1.9, it's easy to calculate if you don't have a calculator. So 1.9 minus 2 is negative 0.1 times 80 plus 32 is actually 24. So if you think about this for a minute, those two y values are pretty close. Notice that this y value is smaller than the actual functional value. And if we think about it, if I'm at 1.9, I'm going to hit the, if you will, I'm going to hit the tangent line first before I actually hit the y value on the function. So the tangent line approximation is smaller than the actual functional value because the graph of the function is concave up. So the tangent line should fall below the graph of the function. Okay, so we should expect that this y value down here is going to be a little bit smaller than, say, this y value right here. So let's plug in 1.99 into the linearization, if you will. So 1.99 minus 2 is negative 0.01 times 80 plus 32. We're going to have 31.2. 31.2 is smaller than this value right here, but notice how close it is. Okay, let's plug in 32. Pardon me, let's plug in 2. I'm sorry, here we're going to get 0 plus 32 is 32. And that makes sense because, you know, that point, you know, they share that point right there, the function and the tangent line. All right, let's plug in 2.01 to the linearization. So 2.01 minus 2 times 80 plus 32 is 32.8. So these y values should be very, very similar. They should be close, but all these y values down here, with the exception of this point of tangency, all these y values should be somewhat smaller than the actual functional values because the graph of the function is concave upward. You would hit the tangent line y value before the function y value. All right, and 2.1 minus 2 times 80 plus 32, let's see, is 40. 40. So these approximations are very, very close to the actual functional values as long as I stay close to the x-coordinate of the point of tangency. I certainly wouldn't want to put like 3. I wouldn't want to put an x value of 3 here because then you're just moving too far away. The tangent line is moving too far away from the graph of the function as it continues to bend and is concave upward. So using a linearization, using a tangent line as a linearization to approximate functional values. Okay, and the big idea I think here that we want to take away from this is, are these approximations from the tangent line equations, are these under or over the functional values? And again, that connection is all towards the concavity there. So try and just kind of visualize concavity and where a tangent line falls with regard to a graph depending upon its concavity, and that will tell you whether these y values are smaller than the functional values or whether they're larger than the functional values.